Okay, good morning. Today's topic is differential equation, mainly first order and second order differential equation. And obviously, the equation which I'm going to discuss, they are linear and homogeneous. I will come to all these phrases, that is linear, homogeneous, in later part. First, what do you mean by a differential equation? A differential equation is an equation which involves differentials of one or more variable, and the differentiation with respect to a single variable or more than one variable. Okay, so these equations are called differential equation. Now, the differential equation can be classified into two categories. One is ordinary differential equation, and the second one is partial differential equation. Now, ordinary differential equation is any differential equation that can involve the differential with respect to one independent variable. That is ordinary. Okay, so in case of ordinary differential equation, the differentiation is made with respect to a single variable. Okay, and this variable must be independent variable. And the partial differential equation is a differential equation that involves basically partial derivative, or the differential equation that involve two or more independent variable. So the second category is known as partial and the first one is known as ordinary differential equation. In this class, I am going to discuss only ordinary differential equation. Now, the first order and second order linear differential equation have the following forms. So this form is the first order differential equation and these are the second order differential equation. Now, if the right hand side of this differential equation is 0, that means this qx is 0, then this differential equation is known as homogeneous differential equation. Otherwise, this equation will be inhomogeneous differential equation. Initially, I am going to discuss homogeneous differential equation, and they must be linear because these are the linear relations. Okay, now before I'm going to start solving differential equation, let us say something about the order and degree of differential equation. The order of a differential equation is the order of highest derivative appearing in this equation. So this d square y and dx square is the highest derivative. Okay, and degree is the power of highest derivative of this differential equation after removing any kind of fractional powers. So let us consider, let us assume that, rather I can say, this differential equation, if contains any fractional power, then first of all those powers should be simplified. After simplification, the highest power of the highest order or the highest derivative appearing in this equation is known as degree. So in this equation, this d square y by dx square is the highest derivative or highest order derivative. So the order is obviously 2, as 2 is appear here, and the degree of highest derivative is also 2. Okay, as 2 is appear here. So this differential equation is basically a second order and obviously second degree differential equation. Now, differential equation will be homogeneous if and only if a differential equation can be simplified in this form. Right hand side will be 0 and m and n are two homogeneous functions of same degree. So if you have any differential equation like this, you have to make this differential equation in this form, and if this mx and nx they are homogeneous function, then the differential equation will be homogeneous. And example of homogeneous equation is given here. X square plus y square first bracket close dx minus 2xy into dy. So this differential equation can be written as dy by dx equal to x square plus y square by 2xy. This shows that the ratio of two homogeneous function of same degree is a homogeneous function of degree 0. Okay. Now first order homogeneous and non-homogeneous equation with variable coefficient. Now if you take differential equation of this form, now if you reduce this differential equation in such a way that the equation can be simplified in this form, where the left hand side is only function of y and the right hand side is only function of x, or I can say the left hand side contains a function of y into dy equal to the right hand side contains only the function of fx into dx, then this equation is a separable equation. And for this, if you consider dy equal to fx dx, this will be the integral solution. So y must be integration fx dx plus c. C is any arbitrary integration constant. Now let us consider an example of radioactive decay. You have already heard that if you put any radioactive material, it is automatically decaying. Let us consider uranium. It is decaying. So assume that at t equal to 0, that is when I just take the part of that uh, radioactive material, then total number of this what should I say, molecule or the uranium atom is there n0. Now if dn number of particle is decaying in time dt, then dnt divided by dt must be equal to number of particles remain at t. So this decay or rate of decay, I can say dn by dt, must be proportional to this nt. Now this equation can be simply written as dn by n equal to lambda into dt. So the left hand side contains only the function of n and the right hand side must be a function of t. So this can be written in this form. Okay, now if you integrate the above equation, this will be integration dn by n equal to minus integration lambda into dt. So on integration I can get this is log n equal to minus lambda t plus c1. So c1 is an integration constant. Now nt is equal to, obviously this will be c1 into e to the power minus lambda t. Now if you want to calculate this c1 here, sorry, this is a typographical mistake, this must be c1. Now these are the general solution. Now you have to calculate this c2 by putting some boundary conditions over this equation. So what are the boundary conditions? We can assume the initial condition as n at t equal to 0 must be equal to n0, which is a constant. So total number of atom present in the parent nuclei. Now n at t equal to 0, this will be n0, and putting n at t equal to 0, this will be n0, and this t will be 0, so this e to the power lambda t will be 1, so c2 must be n0. Now this equation becomes nt equal to n0 e to the power minus lambda t. So this equation can be solved. Now what are exact differential? Consider a function of x and y, and this function of x and y have continuous derivative such that this fxy equal to constant. Now the total derivative of this function must be 0, so df will be equal to 0, and this total derivative df can be written as del f by del x into dx plus del f by del y into dy, and obviously as c equal to constant, total derivative of this equation will be 0. So I can write del f by del x as mxy and del f by del y as nxy. So mxy into dx plus nxy into dy equal to 0. So mxy equal to del f by del x and nxy equal to del f by del y. Now it is assumed in such a way that fxy has continuous first derivative. So as fxy have continuous first derivative, now if you differentiate this equation with y and take a partial derivative, obviously, so del m by del y equal to del square f by del square del x del y, and del n by del x will be del square f by del x del y. So both of the right hand side will be same, so del m by del y equal to del n by del x. So if any differential equation or any function have continuous derivative and it is exact differential, then this equation must be satisfied, del m by del y equal to del n by del x. Now determine, I'm taking an example, determine whether the following equation is exact or not, and find the solution of this exact differential equation. Consider the differential equation in this form. Within the bracket I can write 4x cube plus 6xy plus y square into dx dy equal to minus of 3x square plus 2xy plus 2. Now if you separate x and y, let us put dy in right hand side. I can write the standard form of this equation as 4x cube plus 6xy plus y square into dx plus 3x square 2xy plus 2 dy equal to 0. And this equation, now I can compare this equation with the initial one, that is mxy into dx plus nxy into dy equal to 0. Now this del m by del y, as this is m, so del m by del y if you differentiate this equation, this will be 6x plus 2y. And if you differentiate this part with respect to x, the del n by del x will be 6x plus 2y. Now the condition of exact differential equation satisfies. So they are exact differential. So f xy equal to c, where m equal to del f by del x and n equal to del f by del y. Now how can you solve this differential equation? So del f by del x equal to m. So I can put this equation as 4x cube plus 6xy plus y square from this part. So del m by del y equal to this. So m equal to this. So m equal to del f by del x. Now f is integration of this. So this will be x to the power 4 3x square y plus y square. And obviously there must be some constant, but that constant will be a constant, but it may be a function of y, because this is partial derivative. So if you differentiate any function of y with respect to x, that will give you 0. So the constant term is here might not be a constant, it will be a function of y. Now from the second equation I can write del f by del y equal to 3x square plus 2xy plus 2. Now fxy, if we integrate, then this will be 3x square y plus y square x plus 2y plus this must be a function of x, because if you take function of x and differentiate this function of x with respect to y, this will give you 0 as its partial derivative. So both of this function of x and function of y is unknown to us. If you look at the form of f in this equation and in this equation, there are some terms common. 3x square y appear here, 3x square y also appear here, y square x appear in this function in this form, y square x appear in this form. So I can simply write initially 3x square y plus y square x. I can write 3x square y plus y square x. And if you compare these two equations, and as fxy must be same, so fy must be equal to 2y and gx must be equal to x to the power 4. Therefore the required solution will be x to the power 4 plus 3x square y plus xy square plus 2y. This must be equal to c. Now take any general first order linear differential equation. So as this is first order differential equation, and the equation can be written as dy by dx plus px into y plus qx, or this is y prime plus pxy equal to qx. Now how can you solve this equation? If the equation is homogeneous, then this qx must be equal to 0. And if equation is homogeneous, then you can assume that yh may be a trial solution of this differential equation. As yh is a trial solution, this trial solution must satisfy this differential equation. So I can write yh prime plus px yh, this equal to 0. So del yh divided by yh equal to minus px into dx. Now if you integrate in both sides, you can get yh equal to constant e to the power minus px into dx. So e to the power minus px into dx may act, or rather I can say must act, as a integrating factor of this differential equation. Okay, Now multiply any differential equation or original differential equation in both sides. If you multiply with integrating factor, that is e to the power minus integration px dx, then you can able to solve this differential equation. So I can divide the method of solution of differential equation into two steps. The step 1 is finding the integrating factor. So e to the power px integration px dx is the integrating factor, and the second part is multiply the original equation with integrating factor to solve this equation. Okay, so as this equation satisfies, so I can write this left hand side as d by dx of y e to the power integration px dx, and if you differentiate, this will be this. So finally I can write left hand side as d by dx equal to y e to the power integration px into dx, and this will be equal to qx integration e to the power integration px into dx. Now we can get, after integrating y into the power integration px dx, this will be equal to integration qx e to the power integration px dx into dx plus a constant. Now you just transfer this form from left hand side to right hand side by putting a minus sign here. So y will be e to the power minus px into dx into integration of this. So you can get the desired solution by taking an integrating factor of the differential equation. Now assume a well-known LR circuit. Now this is an inductor and this is the resistance. This is obviously a DC battery. They supply E amount of EMF to the circuit. Now due to application of this EMF, there will be some voltage or back EMF developed in this inductor, and that EMF will be L into di dt. This will reduce basically effective EMF of this battery. So if R amount of current is flowing through this circuit, then I can write E minus L di dt equal to IR, or L di dt plus IR equal to E. You can apply Kirchhoff's circuital law here, or Kirchhoff's voltage law, KVL. You can get the same equation. Now the boundary condition is at t equal to 0, I must be 0. So the standard form of this differential equation is di dt plus I into R by L equal to E by L. Now if you compare this equation with this equation, you can get that Px is equal to R by L and Qx equal to E by L. Now from that differential equation, without solving, I can say that e to the power integration minus px into dt, or in this case px into dx, or pt into dt, that is e to the power minus r by l into t, must be an integrating factor. So the current at any time t will be e to the power minus RT by L into integration E by L e to the power minus R by L into dt plus constant to the power minus R by L into t. Now if you integrate this term, this exponential term give you E by L into L by R. So this will be E by R plus C into e to the power RT by L. Now if you put this boundary condition here at t equal to 0, so this term will be 1. So C will be equal to minus E by R. Now the current will be in this form, E by R 1 minus e to the power minus R by L into t. Okay. Now you can take a well-known Jacob-Bernoulli's equation. This will be a first-order differential equation, and this is obviously non-homogeneous equation. Now the equation have the form y prime plus pxy equal to qx into y to the power n, where n is not equal to 1. So initially you have to transfer this equation in a simplified form, and for transfer let us take a new variable z, and this new variable equal to y to the power 1 minus n. Now if you put z equal to y to the power 1 by n, or y equal to z to the power n minus 1, and if you differentiate z with respect to y, you can get, with respect to x, you can get del z by del x equal to 1 minus n y to the power minus n into y prime. And if you substitute this in this equation, you can get 1 minus n y to the power minus n y prime plus 1 minus n y to the power 1 minus n into px equal to 1 minus n to qx. In this term, the new variable, if you put the new variable as z, so this will be z prime, this will be z, and this remains as it is. Now px must be equal to 1 minus n into px. Okay, so the solution of this differential equation by taking an integrating factor z equal to the power 1 minus n into e to the power minus px integration 1 minus n qx e to the power 1 minus n into integration px dx into dx plus c to the power minus 1 minus n into px dx. Now solve this differential equation. This is another example. You have to change the variable y prime plus x equal to y by x. So in standard form, this equation becomes y prime minus 1 by x into y equal to minus x. So px will be minus 1 by x, qx will be minus x. Now we apply the integrating factor and just solve this equation. Now superposition theorem. Let us consider a nth order differential equation. If you choose a first order differential equation, that equation have only one root. If you take second order differential equation, then the equation must have two roots. If you take nth order differential equation, the differential equation must have n roots. Now, if any second order differential equation have two roots, that is y1 and y2, any type of linear combination of y1 and y2 must be another solution of this differential equation. So if you take y equal to c1 by 1 plus c2 by 2, then y must be solution of differential equation y double prime plus pxy prime plus qxy equal to 0. And there exists another theorem. A necessary and sufficient condition that a differential equation of this form have two solutions y1 and y2, then determinant of y1 and y2 and y1 prime and y2 prime, this should be exist. That is, differentiation of this y1 and y2 must exist. If this should not be 0 or this will not be 0, then y1 and y2 is called they are linearly independent, and this form is called the Wronskian. Now Wronskian have specific importance for solving or finding second root of any differential equation or determining the linear dependency or independency of this equation. Now, second order homogeneous differential equation. So what is second order homogeneous differential equation? The right hand side must be 0 and the highest order derivative will be 2. So these are the second order differential equation. Now I can change this differential equation into a operator form, that is d equal to dy dx, and the characteristic equation can be written as d square plus p0d plus q0 equal y equal to 0. This equation is called characteristics or auxiliary equation. Now how can you solve this differential equation? As this is second order equation, so this quadratic equation must have two roots. You can take y equal to e to the power mx as the trial solution and put y equal to mx here. You can take an auxiliary equation, and from this auxiliary equation you can solve m to get two roots in this form, e to the power ax and e to the power bx. Any linear combination must be another root. So y equal to c1 e to the power ax plus c2 e to the power bx must be the root of this differential equation. Now, one case, if these two roots are different, they are not same, then the solution will be this, and this solution is called complementary function. Now the case 2, and sometimes both the root will be equal. and they are real, obviously. If they are real and they are equal, then I can write d minus x into d minus x a, d minus a into d minus a, y equal to 0. So one solution of this differential equation must be e to the power ax with some constant. Now if this is the solution, then the second solution will be u equal to d minus a into y2. If you put d minus a into y2 where, this will be another solution. So d minus a into u equal to 0 is another solution. Now u equal to c4 e to the power ax. Now okay, so the solution will be u equal to c4 e to the power a into x. Now as you see in the first equation, d minus a into u equal to 0. So u equal to c4 e to the power minus e to the power into alpha a, then d minus a y2, that will be equal to c4 e to the power alpha a into x. Okay, now the equation becomes y2 prime minus ay2, this equal to c4 e to the power ax. Now if you solve this equation by integrating factor method, here px will be a and qx will be c4 e to the power a into x. So the solution will be c4x plus c5 e to the power ax. Now if there exist two equal roots, then this solution will be ax plus b into the power ax. Now take any linear differential equation with constant coefficient, that is obviously inhomogeneous equation. So d to the power n y by dx to the power n plus p1 d to the power n minus 1 y dx to the power n, in this form pn into y equal to x, where this p1 p2 pn are the constants or the function of x. Okay, now if the derivative of the highest order, here it is d to the power n y dx to the power n, has a coefficient other than unity, then the members of equation can be divided by this coefficient and the equation will be treated as this one. Now recapitulate the topic of previous part. This equation have n number of solution, and the solution, any linear combination of this solution must be another solution. So ciyi, that is n number of solution, must be a complementary function, as I have said earlier. But if y equal to u be a solution of 1, then y equal to a capital Y plus u is also another solution, and this u is called particular integral. So complete solution must be a complementary function plus particular integral. Now in case of complementary function, you can solve and you can find complementary function easily by putting y equal to the power mx, as I said earlier, and just you take an auxiliary equation in this form and solve this auxiliary equation to get the values of m or the solution of m. Now you put this solution of m together in the form c1 summation of ci e to the power mix, and you can get the complete solution. Now for an example, I can write this equation d to the power y by dx square plus 3 dy dx minus 54y equal to 0. You take middle term factor, 54 equal to 6 into 9, So two solution, one will be -9 and another will be 6. So they are different. So the complementary function must be equal to a1 e to the power -9x plus a2 to the power 6x. Now if the roots are same, then general solution will be y equal to the power m1x c1 plus c2x plus c2x square c1x plus c2x square in this form. I take another equation, d square plus 8d plus 16 y equal to 0. Now here you get two same solution. m1 equal to -4. Sorry, I have written this +4, but this will be -4. So as this will be -4, then solution y equal to e to the power, obviously e to the power -4x c1 plus x into c2. So for m number of roots, I can write the form of this differential equation, the complete form of this differential equation in this form: d minus m1 into d minus m2 up to d minus mn equal to 0. But when this right hand side x will not be 0, if there exists some x here and this x will not be 0, this will be inhomogeneous equation. Now for inhomogeneous equation, you have to solve this differential equation. You can assume x equal to 0 to derive complementary function, but particular integral can be determined applying different formulas. So in case of this complementary function can be calculated by assuming y equal to the power mx, and m will be some alpha and beta. So complementary function will be c1 e to the power alpha x plus c2 to the power beta x. Particular integral, if this differential equation can be written in this form, that is fd function of differential into y equal to x, then y must be fd to the power inverse into x, so 1 by fd into x. So this will be particular integral. Now particular integral if in this form, then this will be d square minus alpha plus beta into d plus alpha beta equal to x. So in this case 1 by d square minus alpha plus beta into d plus alpha beta into x, this will be particular integral. So 1 by d minus alpha into 1 by d minus beta. Now I can write 1 by alpha minus beta into 1 by d minus alpha minus 1 by d minus beta. Now we can apply integration to get the solution. So method of finding particular integral. Say if d can be written in this form, then particular integral obviously 1 by d minus m1, 1 by d minus m2 up to 1 by d minus mn into x. So this will be 1 by d minus m1. For this last part, you can say e to the power mnx into integration e to the power minus mnx into dx, and taking successive integration, you can get the complete particular integral in this form: e to the power m1x e to the power m2 minus mn into x up to this. Now decompose. So you have to decompose fd. That is the first motto to finding the particular integral. Now decompose fd in this form, where n1, n2, n3, n should be determined. Now if we decompose this, particular integral will be n1 to the power m1x integration to the power minus m1x into x dx. So applying this formula, I can get the complementary function here. Now suppose these are the equation: d square minus 5d plus 6y equal to e to the power 4x. Now decompose this equation, d minus 3 into d minus 2. So complementary function of d minus 3 is e to the power 3x, and complementary function of d minus 2 e to the power 2x. So y equal to this other complementary function, and particular integral 1 by d minus 3, 1 by d minus 2 to the power 4x. Now this can be written as 1 by alpha minus beta, so 3 minus 2 equal to 1. So 1 by d minus 3 minus 1 by d minus 2 e to the power 4x. Now as this equal to 3, the integration or the integrating factor will be e to the power 3x. So particular integral in this case e to the power 3x into integration e to the power minus 3x e to the power 4x into dx, and in this case e to the power 2x e to the power minus 2x into the power 4x into dx. So this will be the complementary function. So this will be half of e to the power 4x. So the total solution must be c1 e to the power 3x plus e to the power 2x minus half of e to the power minus 4x. Now finding particular integral in some special case. Say x equal to e to the power ax, a special form of x. Then if y into y equal to x, so y equal to 1 by fd into x, and fd x equal to the power x. Now if you put d, if you replace d by a, you can get the particular integral. So the rule is that y equal to, if this in this equation x will be to the power ax, then complementary function is 1 by f of a e to the power ax. Now if a is 1 root of fd, if a is 1 root of fd, then fa will be 0, and if a will be 0, then fd equal to d minus a into phi d. So 1 by fd it is equal into the power ax, that will be 1 by d minus a 1 by phi sum a into the power x. So 1 by d minus a into 1 by phi a into the power x. So phi a is the factor remain after separating d minus a from this fd. So the solution will be 1 by phi a, that remains out, 1 by d minus a to the power x. So this will be x into the power x. So this phi a, if you separate this d minus a from phi a, this must be a differential of this fd with respect to d. So this will be x into the power x into f prime d. Now if a is double root of fd, then this will be x square e to the power x f double prime a. In the similar form, put d minus a square here, so this will be psi d. Psi d must be double derivative of f prime d or fd. Then this equation will be this. Now if x equal to x to the power m, where m is any positive integer, then 1 by fd into x, that will be fd inverse into x. So f d inverse into x to the power m. Now you can apply binomial theorem to expand this term fd, and after expanding this term in binomial theorem, you can reduce this by moving the unwanted terms. Then apply differentiation over this x to the power m, and you can get the desired particular integral. Now if x equal to sine x or cos x, any one of these two, then d sine x equal to a cos dx and d square sine x equal to a square sine x. So similarly, d to the power 4 equal to d to the power 4 sine x, or minus a square whole square into sine x, and d square to the power n equal to sine x, so minus a square into the power n into sine x. Now if x equal to sine x, then phi d square sine a square, this must be equal to phi minus a square sine a square, as you get here in this form. So you can write that 1 by phi d square into sine x equal to 1 by pi square into sine x. So particular integral in that case where x equal to sine ax or cos ax, this will be 1 by phi into minus a square into cos ax. Now there is an example. Solve this differential equation. If you solve this differential equation, I can write this differential equation in this form: dq plus capital D square minus d minus 1 y equal to cos 2x. Now the particular integral is just 1 by dq plus d square minus d minus 1 into cos 2x. So this will be equal to 1 by d plus a into 1 by d square minus 1 into cos 2x. Now you can just multiply d minus 1 at the denominator and the numerator of this differential equation. So this will be d minus 1 into d square minus 1 whole square into cos 2x. So I can get d square here. So put minus 2. So this will be minus 4 minus 1 whole square. So this will be 25. And just apply differentiation, that is d minus 1 cos x. So first differentiate this cos x with d. So this will be minus 2 into sine 2x minus cos x. So the equation or the particular integral will be 1 by 25 2 into sine 2x plus cos 2x. You can get complementary function in the similar way as I have derived earlier. Now in the fourth case, where x will be e to the power ax into v, where v is some function of x, then differentiation of e to the power ax into v, this will be e to the power ax d into v plus a e to the power ax into v. So this will be e to the power ax bracket a within the bracket d minus d plus a into v. So d square e to the power ax into v, this will be again e to the power ax d plus a whole square into v. Just initially differentiate this part, we can get this, and second time derivative we can get this. So this will be reduced in this form. So a corollary can be derived from this assumption, or from this fact, that d to the power n e to the power ax into v, this will be e to the power ax d plus a to the power n into v. So f d into e to the power ax into v in this form, just replace this d with d plus a. You can separate this e to the power ax from this term, and you can get e to the power x f d plus a into v as the particular integral. Now apply this function over d to get the particular integral. Now if f into d plus a v equal to v1, then v must be equal to 1 by d plus a into v1. Now substitute v in 1, you can get ft to the power x into 1 by fd plus a v1 equal to e to the power x into v1. Now operating both sides with 1 by fd, you can, and transposing the fact, you can get 1 by ft to the power x into v1. This will be 1 a e to the power ax 1 by fd plus a into v1. Now solve this differential equation. D square plus 1y equal to x e to the power 2x. Now particular integral is 1 by d square plus 1 x to the power 2x. Now put it to the power 2x here and replace d by d plus 2. So this will be d plus 2 whole square plus 1 into x. So e to the power 2x 1 by d square plus 4d plus 5 into x. So e to the power x, just take to the power, this will be to the power minus 1. Now apply binomial theorem to separate this. Okay, you can get 5 minus 4d minus d square in this form. As this is x, I can separate the non-relevant term or irrelevant terms, that is the higher power of d square plus 4d, and I get solution as e to the power 2x by 25 5x minus 4. So I can take some fundamental laws of second order differential equation, that is, if second order differential equation in this form, there exist some fundamental laws. The laws are distributive law. If u and v are two solutions, then du plus v equal to du plus dv. Second is index law, that is d to the power m into d to the power n u equal to d to the power m plus n into u. If k equal to constant, then d k into u equal to k into du. If d, obviously d does not commute with u, so d into u into v is not equal to u into dv. So don't make this mistake. And the inverse operator exists, u equal to dv, so v can be written as d to the power minus 1 into u. D to the power minus 1 is just an integration. So with this part, I am ending. Hope this will be helpful for your further reading. Thank you. Now the Wronskian. Say these are the form of any differential equation, that is a d to the power n a1 to the power n minus 1 plus in y equal to 0. Now y1, y2, y3 up to yn are the real function, and these are the roots of this differential equation having n minus 1 derivative in an interval. So as they are the root of this differential equation, then determinant, this determinant can be defined as y1, y2 up to yn. y1 prime, that is first order derivative of y1 with respect to x, y2 prime up to yn prime, to this y1 to the power n minus 1, that is n minus 1th derivative of y1, and y2 to the power n minus 1, yn to the power n minus 1, these are called Wronskian. Now the function y1, y2, yn are said to be linearly dependent on some interval if and only if the Wronskian are 0. If w equal to 0, they are linearly dependent. Now assume an example e to the power ax sin bx and e to the power ax cos bx. Are they linearly dependent or independent? To find this, let us consider y1 equal to e to the power ax sin bx and y2 equal to e to the power ax cos bx. If you differentiate, this y1 prime will be a to the power x sin bx plus b to the power ax cos bx, and y2 prime will be a to the power x cos bx minus b to the power ax sin bx. Now put this form into the Wronskian and you get the you get the value of w equal to minus b to the power 2ax. So this will be not equal to 0. So y1, y2, they are not independent at all. So the Wronskian basically determines whether the functions are dependent or independent of linearly dependent or independent. So the roots of differential equation will be determined in such a way. I have taken the help of this 3 book to compose my complete topic. One is very good book in mathematical physics by H.K. Das. For first part of this talk, I'm using this H.K. Das, and most of the equations are taken from these books. Second book is very good book, once again Emil Bosch, and the third is obviously Differential Equation by Murray. This is another excellent book. So thank you.